To finish off this section, we're going to be talking about two different theorems. So the first one is called the Morphs Theorem, and the other one's called the Nth Root Theorem. So the first thing is the Morphs Theorem. So what the Morphs Theorem is saying is that let's say you have this complex number in polar form, and let's say you want to raise it up to a bigger power. So let's say I have like 1 plus I raised to the power of 10. Then basically you don't need to continuously be multiplying it 10 different times. All we just can do is basically whatever the number you're raising it to, you're going to raise the R value by that, and then you're going to multiply the values of theta by n, which is whatever the power was. Okay, which is actually pretty neat. You don't have to do that over and over again. And then we have something called the Nth Root Test, which basically says that the nth root of a complex number in polar form, we tend to use these two different formulas. Well, only one of them. It really depends. So basically, if you raise it to the power of 1 over n, then r also gets to the power of 1 over n, and also gets multiplied by 1 over n, kind of like the same thing as a consequence of the Morphs theorem. And then you have an extra plus 2 pi k here. So this is in case you have it in radians. And then if you have it in degrees, you're going to have the second one. So it really just depends. You can see that there's a 360 right there. And this kind of makes sense because remember that when we're talking about roots, we basically are talking about problems that kind of look like this. And we kind of, when we looked up polynomials, we saw that if you have a degree 2 polynomial, you can have 2 roots. Same thing as if you have a degree 7 polynomial, and you're solving for something, then you're going to have 7 roots. Okay, so that's basically what that's saying. So these tell you all the different types of roots that you're going to get. So you have to do them continuously, try to figure out what all of them are. And the way that we do that, it really just depends on what n is. So here, your value of k is going to start at 0, 1, 2, go all the way until you get to n minus 1. Okay, so that's how k is going to work. All right, so let's first start off with the Morphs theorem, and then we'll do the nth root. So here, let's say, so let me give you this example. Oops. So the example would be use the Morphs theorem to find the following. Okay, so basically what we have, we're going to have z is equal to negative square root of 3 plus I to the power of 6. So let's say we have this particular problem. So you have this complex number, and you're going to be foiling everything out 6 different times. So obviously that's not going to be pretty nice to do. Okay, so instead what we're going to use is use this polar form. So the first thing that we kind of want to do is find the polar form of this complex number. And the second thing that we want to do is use the Morphs theorem. Okay, so the first thing that we are going to do is find the polar form. So the polar form is going to be finding the r value. So r is equal to the square root of this negative square root of 3 squared plus this 1 squared. So this is going to be the square root of 3 plus 1, which gives me the square root of 4, which is going to give me 2. Okay, so that's our r value. And then we're going to find our theta value. So theta is going to be equal to inverse tangent of 1 over negative square root of 3. Okay, so then when I put that in my calculator, or you can look it up in the unit circle, because this is a number that's going to be in the unit circle, what you're going to end up getting is you're going to be ending up with negative pi over 6. Now notice that this is not what we want, okay? Because if you look at where exactly this guy is in, okay, so here's negative square root of 3 and here's I. So you can see that this is in quadrant 2. This guy, negative pi over 6, is going to be in quadrant 4. So in order for me to figure out what the angle is, all we got to do is just add pi radians. So I'm going to add pi radians to that, and you're going to end up with 5 pi over 6. Let's go ahead and put it in polar form. So we know that z is equal to r. So r in this case is equal to 2 the cosine of 5 pi over 6 plus I sine of 5 pi over 6. Okay, so that's going to be that guy. All right, so we found it in polar form, so that was the first step. Now we're going to use de Morphs theorem. So basically what de Morphs theorem says is that if I'm raising this complex number to a power, I'm going to take the r value, the radius, and take it to that power. And then the theta value, I'm going to multiply it by whatever the power is. Okay, so in this case, what do we want to raise it to? We want to raise it to the power of 6. Okay, so z to the power of 6 is going to be equal to, so the 2, you're going to raise it to the power of 6. You have cosine, this guy, you're going to multiply the angle by 6, plus I sine 6 times 5 pi over 6. Okay, so now what we're going to do, we're going to go ahead and multiply this out. So when I take 2 and I raise it to the power of 6, that's going to give me 64. And then in the inside, I'm going to get the cosine of 5 pi plus I sine of 5 pi. Okay, so this essentially would be the answer, but since I want to FOIL everything out, since I want it in a complex form, let's go ahead and figure out what this guy's going to be. So now the cosine of 5 pi is just going to give me -1. And then the sine of 5 pi is just going to be 0. So when I solve for this, I'm going to get -64. That's going to be my solution. Okay, so basically what this means is that if I were to continuously FOIL this 6 different times, I'm just going to get -64. So I'm not going to go ahead and FOIL this 64 times. We're just going to say this is the answer. 6 times, I'm going to say that's the answer. Okay, so that's kind of how you use your Morphs theorem. Now, if you wanted to use the Nth Root Theorem, basically what you're doing, what's different about the Morphs theorem is that now you're essentially taking a root of it. So you're taking the square root or the cube root or the fourth root. And the way that we're going to do it, we're going to use 2 different problems. Okay, so the first problem, so let me go down, is going to be the following. We'll find the cube root of z when z is equal to 27 cis 240 degrees. So let's work with degrees now. So here you want to find the cubed root of this guy. Okay, so if I take the cube root, so notice this is a complex number, so you basically want to take the cubed root to both sides. So if you think about what the cubed root means, the cubed root is just basically this, the cubed root of z. So that's basically z to the 1/3. Okay, so how are you going to do that? Well, you're going to take z to the 1/3. Well, that's just going to be equal to r, take 1/3 power to that. Then you're going to take the cosine, take theta, and then put the 3 on the bottom because here n is equal to 3. Plus, since we're working with degrees, it's going to be 360k over 3. Plus I sine of theta over 3 plus 360k over 3. So all I'm really doing is that if you look at the formula for the nth root, I'm just taking the value of theta and dividing it by n. And in this case, it's going to be the denominator of whatever my root is, which in this case is going to be 3. I'm using this guy because we have the degree sign. We don't have the radians. Okay. So now theta in this case is going to be 240. So r in this case is 27, so it's 27 to the 1/3. Then cosine of 240 over 3 plus 360 divided by 3, that's going to give us 120. Plus I sine of 240 over 3 plus 120. Oh, I forgot the k. Okay, so now 27 to the power of 1/3 is going to be 3. Then you're going to have the cosine of 80 degrees plus 120k plus I sine of 80 degrees plus 120k. All right, now this is not the answer because what you want to be able to do is you want to go ahead and iterate the values of k. So remember, k goes from 0, 1, and then continues on to until you finish to n minus 1. Well, n in this case is equal to 3 because that's the denominator or the root. So 3 minus 1 gives me 2, which means you're going to have all the 3 solutions are going to be 0, 1, and 2. So that's how I'm going to find all my 3 roots. So plug in the values of k equals 0, 1, and 2. So we're first going to start off with k equals 0. So we're going to have 3 cosine of 80 plus 120 times 0 plus I sine of 80 plus 120 times 0. Okay, so notice this is going to go away, so you're left with 3 cosine of 80 degrees plus I sine of 80 degrees. Okay, so at this point, this is going to be the answer, but if you want to tell me actually what the approximate answer is, you're going to take the cosine of 80 degrees, so make sure that your calculator is in degrees. So this is going to give me, let's round it to 2 decimal places, so this is going to be 0.17 plus I, then we're going to take the sine of 80 degrees. That's going to give me 0.98. And then let's multiply this out. So you're going to have 3 times 0.17. That gives me 0.51. Plus, and then 3 times 0.98. That's going to give me 2.94. And this is I. So this is the complex number, the first complex root. Okay, so if I were to take the cubed root of this is going to be the first root. Okay, so now we're going to do it for k equals 1. And when k equals 1, we're going to do the same thing. 3 cosine of 80 plus 120 times 1, which is 120, sine 80 plus 120. Okay, so now 80 plus 120, that gives me 200. So we're going to take the cosine of 200 degrees. That gives me negative 0.94 plus I, and then you're going to take the sine of 200 degrees. That's going to give me negative 0.34. Okay, and now let's multiply this together. So 3 times negative 0.94, that gives me negative 2.82, and then 3 times negative 0.34, that gives me negative 1.02, and this is I. So now this is the second root of this complex number. And now we're finally going to stop at k equals 2. So we're going to have 3 cosine of 80 plus, now we're going to take 120 and multiply that by 2. That's going to give me 240 plus I sine of 80 plus 240. So I'm now going to take the cosine of 240 plus 80. So 240 plus 80 is just going to give me 320. So I'm going to take the cosine of 320. And I'm going to get 0.76 or 0.77. Okay. And then I'm going to add this to the sine of the 80 plus 240. That's going to give me negative 0.64. So when I FOIL this out, I'm going to get 3 times 0.77, which is 2.31, minus 3 times negative 0.64, it's going to give me 1.92. So this guy right here is going to be my third root, okay, of that guy. Okay, so there's 3 different roots. So this one is a little bit involved because there's a lot of things that you got to do because of this iterative method. And basically what it's kind of telling you is that you can kind of see where all the roots are in the complex plane. The first one is in like the first quadrant. The next one is going to be in quadrant 3, and the other one's kind of like in quadrant 2. So you can kind of see, like, if I were to kind of just like imagine that this is the solutions, we have a special name for them in complex analysis, but they basically look like some sort of shape, which is a triangular shape in this case because there's 3 roots. So you don't need to know that. That's fine. But let's just do one more problem. Okay, just to finish up. So find the 3 roots to z is equal to, or z cubed is equal to 8. Okay. So basically what you want to do is figure out what the 3 roots are. We know that this is a degree 3 polynomial, if you want to call it like that. And we know that we're guaranteed 3 different roots by the fundamental theorem of algebra. So easily we can take the cubed root of this and you can see that the answer is 2, but that's only 1 root. Okay, what are the other 2? That means that the other 2 must be complex. Okay, and we don't have like a cubic formula that we can try to do. I mean, we do, but we're not talking about that. All right, so what we're going to do is we're going to convert this to polar form. Okay, so we're going to use this number 8 to kind of convert that into a polar form. Okay, so first let's find the radius. The radius is just going to be the square root of a squared, which is going to be 8 squared, plus there's no imaginary part, so it's just 0 squared. So it's going to be, just give me 8. That's going to be the r value. Theta is going to be equal to the tangent inverse of the y value, which is the imaginary part, which is in this case going to be 0 divided by 8. Okay, so then you just start taking the tangent inverse of 0, which in this case gives me 0. Okay, and that makes sense, right? Because if I was looking at the axes, you can see that a is in this direction. Okay, so here's the point. Here's when theta equals 0. So that kind of just makes sense. Okay. All right, and now we can write it in this particular form. So we know that z cubed, in this case, is going to be equal to the r, which is going to be 8. And then we're going to have the cosine of 0 degrees. Oops. Of 0. Let's just write it in degrees, just for the sake of it. Plus I sine of 0 degrees. Okay, so this is basically the polar form of this guy. So I just replace this guy with the polar form. Okay, now what we want to do is we don't want that. We want to find the cubed root. Okay, so the way that we find the cubed root is that we're just going to take the cubed root to both sides, essentially. So if I wanted to take z cubed, well, I'm going to take the cubed root to this side. And basically, this 8 is going to have a 1 over 3. And then this guy is also going to have the cosine of 0 degrees plus I sine of 0 degrees to the power of 1/3. And if you remember, if I want to have this 1/3 here, then all we have to do is use that iterative method that we just learned to try to figure out all the different roots. So this is going to be 8 to the 1/3, which in this case is just 2. We're going to have cosine of 0 degrees over n. So what's n in this case? So n is going to be equal to 3 again. Okay, 3 plus, we're working with degrees, so it's 360k over 3 plus I sine of 0 over 3 plus 360k over 3. Okay, so here you can see that this is just going to go away. So I'm left with the cosine of 120k plus I sine of 120k. All right, so now we have to do the iterative method, right? So notice that n here was equal to 3, so that means k is going to go for 0, 1, and 2 again. So we're going to start off with k equals 0. Okay, so we're going to take 2 times cosine. This is going to be a big fat 0, I sine of 0. So this is going to go away. This is just equal to 1, so 2 times 1 gives me 2. So this is my first root. And that kind of makes sense because and we kind of already knew that, because if I take the cubed root of this, I'm just going to get 2. Okay, so that was one of the solutions that we already knew. So now let's say we wanted to do it when k equals 1. So what's going to be the second root? So we're going to take 2, then we're going to take 120. Oops, I forgot the cosine. So cosine of 120 degrees plus I sine of 120 degrees. Okay, so we're going to start off with cosine of 120. You can look that up in the unit circle. That's going to be negative 1/2. And then you're going to take the sine of 120 also, and you're going to get square root of 3 over 2. So when I FOIL this out, you're going to get negative 1 plus I square root of 3. So this is my second root. It's actually a complex root, okay? And now we're going to look at the last one, which is k equals 2. So you are going to take 2 cosine of 120 times 2. So 120 times 2 is going to be 240 plus I sine of 240. So now the cosine of 240 is going to be negative 1/2. And then we're going to take the sine of 240. That's going to give me negative square root of 3 over 2. So then this is just going to give me negative 1 minus I square root of 3. This is our third complex root. So basically what this means is that if I were to plug in any of these numbers, including the complex, and I plug them into the original, into z, and I cube it, then I'm going to get 8. So that's basically how you solve these types of problems.